Good morning, students. In this video, we're going to discuss about the transport level security. Module 1, transport level security, TLS. What actually a transport level security TLS is? A TLS is an IETF standardization initiative whose goal is to produce an internet standard version of Secure Socket Layer (SSL). The transport layer security is defined as a proposed internet standard in RFC 5246. RFC 5246 is very similar to that of SSL version 3. The same record format as like the SSL record format is followed in the TLS also, which have been defined in the RFC 2246. Hence, we can say that TLS is similar to that of SSL version 3. Let's we highlight some of the difference in TLS when compared with the SSL version 3. The first one, version number. The TLS record format is same as that of the SSL record format, and the field in the record header have the same meaning as like the content type, major version, minor version, and the compressed bytes. The only difference in this version value for the current version of TLS, the major version is 3 and the minor version is 1, whereas in the SSL version 3 minor version is 0. Here the minor version is 1. That is the major difference between the SSL and TLS. Let's see the second one, message authentication code. There are two different differences between the SSL version 3 and TLS MAC scheme. The actual algorithm and the scope of the MAC calculation. The TLS makes us of HMAC algorithm defined in RFC 2104. Hence, the HMAC is defined as HMAC of M is equal to HK plus XOR with the particular operand, and which have been concatenated with an I padding and concatenated with the message. Whereas the H is nothing but the embedded hash function for TLS. Either it may be an message digest or an SH1. M is nothing but the message input to the HMAC, and K plus is nothing but the secret key padded with zeros, and I pad is nothing but the zeros, 36 in hexadecimal, and O pad is nothing but 5C in hexadecimal, which repeats 64 times as 512 bits of the data in the particular MAC padding data. The SSL version 3 uses the same algorithm, except that the padding bytes are concatenated with the secret key rather than being XORed with the secret key padding to be the block length. The level of security should be about the same in both cases. For the TLS, the MAC algorithm calculation encompasses the fields indicated in the following expression as MAC write secret sequence number, which is going to be concatenated with the TLS compressed dot type, and which have been concatenated again with the TLS compressed version, and which have been concatenated with the TLS compressed length and concatenated with the TLS compressed fragment. The MAC calculation covers all of the fields covered by the SSL version 3 calculation plus the field TLS compressed dot version, which is the version of the protocol being employed. Let's see about the third one, pseudo-random function. How the pseudo-random function is going to be worked over here. Here, the TLS makes use of a pseudo-random function referred to an PRF to expand secrets into block of data for purpose of key generation or validation. The objective is to make use of relatively small shared secret value, but to generate longer block of data in a way that is secure from the kinds of attacks made on hash function and MACs. The RFC is based on the data expansion function. Let's see the data expansion function with a small animated video. The HMAC data, the seed and secret key both are going to be get hash function, which is going to be created in HMAC data, that is going to create with a concatenation of a seed again, which creates one more HMAC data to produce the length, and that the first level of seed and secret produces an A1 data, which is going to be creating the second level of A2 data, and meanwhile it is going to provide the third level of data, and such a way it goes on and it's going to produce the length of the hash value. Let's discuss how this function is going to be. The RFC is based on the data expansion function, which have been given as p hash of secret comma seed produces an HMAC hash of secret A1 concatenated with seed and concatenated with HMAC of hash secret comma A2 concatenated seed and concatenation with HMAC of hash secret comma A3 concatenate with seed and concatenate goes on, whereas A of is defined as A of 0 is nothing but seed, A of I is nothing but HMAC of H secret comma A of I minus 1. The data expansion function makes use of HMAC algorithm with either message digest 5 or SHA1 as the underlying hash function. As can be seen, HMAC can be iterated as many times as necessary to produce the required quantity of data. For example, if PSHA1 was used to generate 64 bytes of data, it would be discarded. In this case, P of MD5 would also have to be iterated 4 times, producing exactly 64 bytes of data. And note that each iteration involves 2 execution of HMAX, each of which in turn involves 2 execution of the underlying hash algorithm. To make PRF as secret or secure as possible, it uses 2 hash functions, and in the way that should guarantee it secured if either algorithm remains secure. So hence PRF is defined as PRF secret comma label comma seed, which defines and which gives an p hash s1 comma label concatenated with the seed. So PRF takes as input a secret value and underlying label and a seed value and produces an output of arbitrary length.